In general, the exactly two outcomes are thought of as a success and a failure. And a success doesn't have to be a good thing. Success just stands for what do you want to see. So some examples of Bernoulli experiments. We've talked about a few of these. If you flip a coin once, you can get heads or tails. Exactly two outcomes, and flips of a coin are independent. Rolling a die once, you get a 6 or not. Taking an exam, you pass or you fail, etc. Now, where the binomial distribution comes in is, well, what if you don't do this just once? What if you flip a coin multiple times? So you have several Bernoulli experiments in a row. They're still independent. Each trial is independent of one another. And what you're measuring then is not just did I see a success or a failure. You want to know how many successes did I see. So we're counting successes. So in any problem or an experiment that has those characteristics, exactly two outcomes, and independent trials, and more generally, you have n trials, so just some number of trials, more than one is assumed. Then your random variable, big X, follows a binomial distribution. This has certain characteristics. It makes the math easier, which means the calculator will start to do the work for us. So if you don't have a TI-83 yet, you need to get one, because we're going to use it now. So let's think about this example. We're going to roll a die or roll 5 dice, and we're counting the number of 5s we see. So we have big X, so we're counting the number of 5s in 5 dice rolls. So little x could be 0, 1, all the way up to 5. And we're interested in creating the probability distribution for this random variable. So what's the chance that we would see no 5s in 5 rolls, or 1, or 2, or 3, or 4, or 5? So let's think about this one. What's the probability that we see exactly 3 5s? So we're asking the question, what's the probability that big X is 3? Because again, big X stands for the number of 5s we see, and we want that to be 3. So this is kind of in the middle of the probability distribution. So we expect that there's going to be more than one way to get 3 5s. Well, it's sometimes hard to think about and find all the different combinations. So here are some possibilities. In our 5 rolls, the 3 5s could come first, and then we'll get something else. Not a 5, not a 5. So if we multiply those probabilities together, 1/6 for getting a 5, 5/6 for getting not a 5, that's the same as doing 1/6 to the third power, because you're multiplying them 3 times, and 5/6 to the second power. Well, another combination, 5 something else, 5 something else, 5, same proportions in a different order, so you get that same result, 1/6 to the third, 5/6 squared. So this lists 3 different outcomes, but there are several. So what we'll come back to is there's a way to figure out how many different combinations are there. And there are in fact 10 different combinations of 3 5s and 2 not 5s. So to find the probability that x is 3, just like before, we'll take the number of ways that we could see that outcome times the probability that one of them occurs. So as we saw above, that's going to be 1/6 to the third times 5/6 squared. And that works out to be 0.0322. So now is where the binomial distribution comes in. If we worked out every single value of the random variable, 0 through 5 by hand, and we had this equation for each different probability, there is a pattern that occurs, and people figured out how to anticipate or how to explain every value that shows up on this side for each probability. So they came up with a general formula to find any of these probabilities. So in a binomial distribution, the probability for any value of the random variable, whatever little x you want, uses this equation. So it looks kind of odd. It's kind of complicated. We won't do it by hand, but we can sort of see the pieces. This first piece, this is not a fraction. There's no horizontal line here. This is a way of denoting combinations. So this piece here gives you the number of ways, the number of combinations you can see. And there's a formula for it, which I'll show you just so you know. So when you have something like this, n, remember, is the number of trials. Little x, that's the value of the random variable you're interested in. So what you're saying, or what you're asking here is, how many ways out of n trials can I have little x successes? So the formula looks like this. Which probably doesn't help things. The exclamation mark is called a factorial. So the way that a factorial works, if you say I want to know 4 factorial, you take 4 and multiply it by every integer less than it. So 4 times 3 times 2 times 1 is 24. So you just multiply a lot of stuff together. So this formula gives you the number of combinations. We won't do it by hand, but that's what it tells you. What comes next is this thing called P. So P, that's the probability of a success. Where you've defined what a success is in your experiment. The exponent is always little x. So little x, that's the number of successes we're interested in. You multiply that by 1 minus p. So this is the probability of a failure. And its exponent is the number of trials minus the number of successes you want. So if you notice, x plus n minus x just adds up to n. So the exponents have to add up to the number of trials you have. And it always follows this format. Combinations, your probability of success raised to the number of successes you want, failures to the number of trials left over. When you have a binomial distribution, there are shorter equations for finding things like the mean and the variance. So we don't have to, for the mean, take each x multiplied by its probability. In a binomial distribution, all that we have to do is take the number of trials times the probability of success. The variance works similarly, you just have to additionally multiply by the probability of a failure. So, what results is a bunch of distributions that look like this. So these distributions are similar except for one aspect. They all use 10 trials, but the probability of success, P, is changing. So here the probability of seeing a success is 10%. Down in the bottom right, there's a 90% chance to see a success on any given trial. And in total, we're doing 10 trials. So if you do something 10 times, and there's only a 10% chance to be successful, how many successes will you see? Well, probably not very many. So the x-axis indicates the number of successes in your 10 trials. So when the probability of being successful is low, then you're not going to have very many successes. 0, 1, 2, 3. You're certainly not expecting to have 10 successes, though it's not impossible. What if the chance that you see a success is 50%? Well, out of your 10 trials, you expect around half of them to be successful. So the tallest bar is when x is 5. 4 and 6 are the same, 3 and 7, 2 and 8. So it sort of tapers off from there. With a 50% chance, you don't expect all 10 to be successful, and you don't expect none to be successful. So all the way on the other extreme, what if you have a 90% chance to be successful? Well, then out of your 10 trials, you should see a lot of successes. So that's why the distribution here is left skewed. With a 90% success rate, you're expected to see 9 successes in your 10 trials. 10 is possible, 8 is less possible, 7 and 6 are even less likely, all the way down to 0. Again, 0 is not impossible, it's just very unlikely to have no successes with a 90% chance of success. So how do we find these probabilities then? If we're not going to use the formula, we don't have to think about all the different combinations, we don't have to use the factorials, well, we have a calculator function. So it's this function called binom PDF. So what that stands for is the binomial probability density function. PDF. So what this does is it gives us the result is an exact probability for some number of successes. So once we get to this function, we have to tell it 3 things. How many trials are you doing? N. What's the probability of being successful? P. And how many successes do you want? Which probability are you interested in? And that's little x. So in this example with the dice, we were trying to find the probability that x is 3. So what we're going to do is do binomial PDF, where n was 5. P, the probability of rolling a 5 on any given trial, was 1/6, and we want 3 successes. So to get to this function, here's what you do. You press the second button, which is this yellow button, plus next you press the vars button, which is next to the down arrow, and then we'll find the binomial PDF entry. So if you've never used a TI-83 before, you'll notice that above each button, some words are in yellow, some words are in green. Well, if you want to access the yellow buttons, you have to press the second button, because it's yellow. For the green, you'll press the green button. We won't use the green button, we'll often use the second. So when we press second vars, that's taking us to this DISTR menu. which is short for distributions. So, we turn the calculator on, press second vars, and you'll see a list of distributions. So you press the down arrow until you see number 0, Binome PDF. So you may notice just below it is Binome CDF. Don't use the CDF. It does something different. We will use PDF. So you highlight it, press enter, and it should show up on your screen. So now we put in our values. N was 5, comma. The comma is above number 7, right here. Now the next entry was P, the probability of success, which was 1/6. And you can enter that as an equation. So you can do 1 divided by 6. It will do the math for you. Comma, how many successes do we want? Well, we wanted 3.